So hi again, everyone. We will get started. Don't worry if you missed the start or anything. It is being recorded and will be available to view. So welcome to the second session in the final webinar in the series brought to you by Exida. Today we're going to be looking at using an FMEDA tool and specifically FMEDAx. So yeah, all through these webinars, we've been kind of building on, obviously starting out with what is an FMEDA, going through all the different aspects of doing an FMEDA, the different metrics to try and capture what makes a good FMEDA. So we're bringing that all together today and kind of culmination of all those other webinars into using an actual FMEDA tool, specifically Exida's own FMEDAx, which is part of the OEMX suite. Slide handouts will be provided, and as I say, the webinar is recorded, so you'll be able to look back on it either on the YouTube channel or on Exida's own website. So it's kind of minor importance now at this stage. This slide, it just shows you where we've started and where we've come to, starting out obviously over 5 weeks ago with what is an FMEDA. So yeah, it's kind of bittersweet. I've enjoyed these webinars. It's great to see the interest from people, so let's get stuck in. Exida was founded over 23 years ago by several of the world's top reliability and safety experts. And as you can see, over those 23 years, the company has really grown to be a truly global company. And many professionals around the world turn to Exida when they're looking for guidance, experience, or even the tools that we're going to look at today to help them do their jobs better, whether it's in certification, functional safety, alarm management, or cybersecurity. So I won't dwell too long on this slide because obviously we're going to deep dive into OEMX and look at specifically the FMEDAx part of the tool. But just needless to say, Exida, there's a few different facets to the company, but one important aspect to the company is that they have their own in-house software development team, and part of that team, one of the products they produce is the OEMX. So we'll look at that now in a few moments. Just a quick recap. Where like the FMEDA comes from, and I suppose a good FMEDA starts with a good FMEA. So you're looking at your product, you're looking at the highest architectural level, the system level, and then you start breaking that down into the sub blocks. Some of those sub blocks may be further broken down into another level subdivision. For example, your power supply may be broken down into low logic level, high voltage, isolation, AC, various different things. So you could break it down even further. Each of those sub blocks, then you describe in your FMEA the failure mode of those blocks and the effect of those failure modes. It's at this point then, when you get to the component level, that the FMEDA kicks in. So what we would do in that example, we're looking here at a power supply. We're doing our analysis. We got a power regulator IC. And what we do then is pull in that component into the FMEDA tool. The failure modes are automatically populated, I should say, into the tool. And also then the failure rates for each of those different failure modes are automatically populated out. You then pick the failure mode that's applicable from the sub-block that you're analyzing for each of the different failure modes for this component. And you do this for each component in your design, and ultimately that's how your FMEDA is done. What we will first look at here is the main OEMX tool. As you can see here, we're in the requirements window. So normally when you're doing your full analysis, the first thing you want to do is you start putting in your specific requirements that you want for your design. This could be a multidisciplinary team effort, and you want to make sure that the requirements translate and are communicated correctly across the entire development team. So in here, you would start putting in your requirements. In the tool, once you right click on a window here, you get a context sensitive menu. So there's nothing in here at the moment, it's blank. We right click and we get two options, add requirement, or import a subtree. I'll explain about importing a subtree in a little while, but needless to say, first thing we want to do is add a requirement. Just a little bit about requirements. Obviously, the requirement attributes, they provide the information needed to understand a requirement. And as I said, misunderstanding at this early stage can cause many wasted engineering hours. Having an integrated requirements manager saves entry time and reduces the chance of requirement omission errors, because obviously multiple people can look at this and all have their own tuppence worth and make sure that their requirements are all fully captured. Integrated validation test definition capability also saves time, as it can be done while in the context of the requirement and much quicker than switching tools. And then requirement tracing is done to show when a requirement has been implemented. And again, this saves project management time. As design changes are made, all requirements implemented by the block can be displayed to verify the change will not negate any requirement. So as I said, we're in here, we've right-clicked, we're looking to add a requirement. And what we do then, once we click on add requirement, we get this screen, requirement node editor. So we edit it. Once we put in here power supply requirement, as you can see, it's automatically captured up here. The next thing we may want to put in here is the type of this requirement. Is it an architectural requirement? Is it derived requirement, market requirement, so on and so forth. The other thing about this particular part of the screen, it's a free form entry, so you can type in whatever you want there. There are some pre-defined requirements there that kind of speed up the process, but if there's one specific to your application, you can type it in there and it'll be saved, and you can pull back on it and use it throughout your project and your analysis. Next thing then, as I said, each of the menus in OEMX tool are context sensitive. So now, because we already have a requirement in, when we right click on this, we get a new menu coming up. So we can add requirement, which would be a sub requirement to this top level requirement, let's say. You can create a new action item. Something to mention here is that you have the ability to call upon the requirement expert knowledge database. And in here, it's a lot of many years worth of expert knowledge that's been condensed into a database that allows you to basically do out your requirements while you have that expert sitting beside you as such. So we'll talk a bit more about that as we move on. So we've entered in all the requirements, and this is what it may look like then once you have all your requirements put in. You have your top level for your product, and then as you move down, you have further sub requirements. Some are specific to maybe your target SIL capability. They could be derived requirements, and so on and so forth. But this is what a finally finished requirement editor may look like. And each of these can be called on as you move throughout the project. The next thing we look at then, as you can see here, we've changed tab. We're now in ArcX. So this is basically the level where we're in to do our FMEA as part of our analysis. So the tree structure is a well-proven technique for showing a structured hierarchical design that has been proven to be quick to understand. As I said, the knowledge base is also implemented in ArcX, and this effectively provides an instant FMEA with failure modes and potential mitigations. And this has been shown to drastically reduce engineering time and increase the FMEA quality, because you have consistency every time you use the tool, and from project to project, you have that level of consistency and reliability. Using a common tool for hardware, software, and cyber saves time by maintaining an established design context, using the same commands and the same tree structure. And then, as I said, we're in the FMEA tool, and we got our top level system in here. So once we can go to the type level, and we can enter in which particular type this top level system is, what type of component, what type of block it is. Again, it's a free form entry, so you can type in whatever you'd like at this particular moment. Using the context sensitive menu, right clicking on the top level, it comes up with a different menu now. So we can add in a unit, which would be a sub block to our FMEA tool, or we can go straight in and start adding in deviations. Again, as I say, in all these context-sensitive menus, you have the ability to call upon the expert knowledge, and for this it would be the deviation expert knowledge. It changes accordingly depending on what part of the tool you're in. So let's assume we've gone through the process, we've added in our blocks in the FMEA, and now we've added in our deviations and mitigations. Some of them may have been manually entered, some may have been entered in using the expert knowledge tool. But needless to say, we've done our analysis on our simple flasher circuit, and here are all our deviations and mitigations. Looking at the first one here, we've clicked on the top level deviation, or the first deviation for our power supply. This is the one where we have a redundant power supply built into the design. So the deviation for power supply A going to 0 volts. What type of deviation is this? This is safety critical, safety related, or whatever you want to enter in there. You put then in the potential impact of this particular failure. Is it a safe fault, dangerous, enunciation, or you don't care? In this particular example, it was designated as being safe because it's a redundant power supply, so the system still works as it should. As you can see there, we put in a few notes just that if someone else is coming along and looking at your analysis, they can understand the reasons why you picked this particular aspect of it. So these other fields here, they're more relevant to the reports, which we'll talk about in a little while. The next thing then we click on is our mitigation. So the mitigation for this particular deviation, basically we describe here whether the diagnostics detect this particular deviation, to what level they capture them, and then the action taken if it's been detected. So that's pretty much it for the FMEA. As I say, it's considerably sped up if you use the expert knowledge, because a lot of these fields and entries are already pre-populated based on years and years and years of expert knowledge. So the next thing we move into now is we're doing our FMEDA, sorry. We've all our information in our requirements. We've all the information, deviations and mitigations into our FMEA. So we start entering in our components and linking the components failures for each of the particular blocks to the failure modes of the blocks that they're contained in. Something to note here, up here we've two little check boxes. This allows you to quickly switch on and switch off the deviations and mitigations for the particular blocks, just if you want a quick reminder of what you designated in these blocks. Instead of having to switch between the tabs, you can look at the deviations and mitigations side by side with your component entry. Again, context sensitive menu, so right clicking on the unit block that we want to enter a component into will now give us the option to add component because we're in the FMEDA mode. So clicking on that, we enter in our first component already. Obviously some are already in, but this time we're adding in an extra component based on our analysis, and we're adding in a transient suppressor. So once we type in the name, it automatically gets translated over into our component window on the left hand side. The next thing we need to do then is basically pick this actual component from the component reliability database. To speed up that process, if you know the exact title of the component, you can start typing it in here in the component filter, or you can use the category drop-down menu. Because this, what we're looking for now is an electrical electronic component, we can now select electrical, and this allows us to then further filter down the components that we look at. The one we're looking at for this particular example is an EMI filter. It could be a diode, whatever is applicable to your particular component that you're selecting at this moment in time. So we click the drop down menu, click the EMI filter, and the next thing we need to do once that is done is we need to now click on the assign CRD button up here. And once we do that, that component now is locked in into the design and assigned to the transient suppressor, and it's pulled, all the information is pulled from the component reliability database. As you can see here, because the information is pulled from the component reliability database, automatically then the total component failure rate for this particular component is populated. It's 2.7 fits, and this is applicable to the exida profile tree, which we'll talk about it again in a few moments. As you can see, the failure modes specific to this component have been automatically filled out for us, and accordingly then the failure rate, contribution and distribution for each of these particular failure modes. Some components have an extra option to select things specific to that component. So for example, with this EMI filter, is it a signal level filter or is it a power level filter? So it allows you to select from drop-down menus, and this accordingly will change the specificity of the component failure rate for this particular component. Obviously, power might have a higher failure rate than a signal level EMI filter. So that all we're left then to do is start selecting the functional failure modes for each of the different failure modes for this component. So again, from the drop-down menu, we can go in, and we could also use this filter option up here, failure filter mode filter, and start typing in power, and that would basically filter out all of the functional failure modes not specific to the power supply block. But assuming we do that, it's very quick to use the drop-down menu. And next thing, what we've done then is we've selected all our functional failure modes for all the different failure types for this particular component. And that's it done for that particular component. It's a very quick process. It may seem a little bit longer while I'm showing it here using PowerPoint, but in practice, it's a very quick process indeed. So the next thing we need to then look at is, obviously we've entered in all our components. What results are we getting? Is this product that we're doing in terms of overall failure rates, are we on target to reach a particular SIL level? So the next thing we need to do is go to the project drop-down menu, click on the FMEDA results window, and up pops this window, the subsystem viewer, which shows us all the different failure rates and all the different failure types for the complete design. As you can see, we then have the option to go into the more details, FMEDA details, and by clicking on this then it gives us the total failures for all the different failure rates again in a different layout. Now the advantage of this particular window is you can see then there's two little check elements built into the OEMX suite. OA and UA, basically over allocated and under allocated, and this will advise you whether you've over allocated to a particular component with its failure rates, or if you've forgotten to assign a failure mode to a component, so then you would have an under allocation. So there are two little checks to make sure and allow you to know that you're kind of on target and that you've entered in each component accordingly. If you haven't, as you can see here, we've over allocated on a particular component. Within this window then, if we zoom in a bit closer, what it will allow you to see is which particular component we have over allocated on. So across the way, you can see a list of all the components within the design, all the different types of failures. And then over here, you can see over allocated and under allocated. So here you can see with the U5 operational amplifier, we've over allocated. So this allows you to dive back into your component FMEDA and look and see why there's an over allocation there. So it's a quick little check to allow you to keep an eye on things. The next thing then that you may want to see is what impact will the change in environmental profile have on your design, whether it will increase the failure rates or reduce the failure rates accordingly. And then, as I explained, you may have some outliers in terms of your customers who want your product, but maybe using it in an unorthodox environment. So this will very quickly allow you to have a look and see what impact that will have on your product design. So if we just click then on the project menu, we go down to the project environmental profile. We've currently got exida profile 3 selected. We're now going to change that to exida profile 1, which is a cabinet mount, kind of lower temperatures, more ambient room temperature type environment. So you would hope and expect to see a drop in some of your failure rates. So if we just keep in mind safe undetected failures are 111.5. By clicking on the new profile, we've seen a drop in our safe undetected, and we've also seen a drop in our dangerous undetected failure rates. Another advantage of the FMEDAx tool and using this subsystem viewer is the ability it shows you to actually compare two different revisions of your design side by side. Now I mentioned at the start with one of the context sensitive menus, the ability to import. So what you could do as you're going through your different revisions of your design, you could save them and export them as a project tree and then re-import them. So if you can see down here in the bottom, up above we've Rev 5, which is the one we're doing the analysis on. Down here we've Rev 4. So by doing this now and going back into our subsystem viewer, we can look and see and compare the failure rates for each of these two different designs. And as you can see here, from revision 4 to revision 5, there's been a massive drop in our dangerous undetected failure rates. So whatever change we've implemented, it's had a positive impact on our design. So without even going to a breadboard, without even going to manufacturing, this very quickly allows you to compare each design and see what impact that may have. So that's the majority of the features of the FMEDAx tool. The next thing we will now look at is some of the other features built into the OEMX suite. So in the file menu, some key features or nice features that it has is this auto backup feature. Now, sometimes you may not want this on, particularly if you have a relatively small space, or if you're using a network share. If you have the software saving on a regular basis to a network share, it might have an impact on the performance of the actual application. So you could switch off the auto backup. But then obviously the positives are if there was a crash, having this switch on means that you will minimize the amount of data and time that you will have lost in a crash event. The next feature that it has is can drag tree nodes. Now, where this comes into its own is if you enter in a block into your design and then realize that you want to change its location within the FMEA tree structure, by enabling this can drag tree nodes, you can then click on the node or the tree and drag it to the exact location you want, and very quickly drag and drop and then switch it off. It's just a very quick and easy way to orientate your particular tree structure and your design. And then finally, enable auto calculation. Again, depending on the abilities and performance of your particular computer that you're using, having this switched on, you may see an impact in the performance of the application. But I suppose on more modern computers, it's not really a factor. So having the enable auto calculation switched on means that if you make a change in your FMEDA, you will see an immediate impact in your subsystem viewer, or basically the output results from your FMEDA. The next menu to look at is the project menu, and in here we've already looked at obviously the FMEDA results and the project environmental profile, whichever one we've selected. The next one we're going to look at is edit the project details, and in here it gives you the ability to basically fine-tune the specifics of this particular project that you're working on. It also enables you to import schematics, pictures, images, anything that's relevant to this design that you feel should be contained within this project file, especially if you're going to transfer it throughout other team members or project members as you go on. Any file that's in here, whether it's an image, a schematic, a PDF, whatever it happens to be, if you double click on it, it'll automatically open up and allow you to view it side by side while you're doing your analysis. The next menu to look at is the reports. As I said, in the FMEA, when we were entering in our deviations, there was a couple of drop-down menus which enable you to, it's a bit like your RPN figure, enables you to basically describe the severity of a particular deviation. Where they become applicable is in this report output for your FMEA summary report. So if we see up here, ArcX FMEA summary report. So this will give you a nicely formatted output report of your FMEA. And as you can see, there's a number of other reports there built into the tool. The next menu that we look at is our expert knowledge. And as I said, this is probably second only to the component reliability database in terms of its value and importance within the tool. Like in here, there's years and years and years of expert knowledge built into it that allows you to very quickly speed up the process of entering in your requirements and your FMEA design. And then the next one is our library. In here, we can look and see our unit library, deviations, action items, all the various different aspects that we've included in our design. Also then reference document library. It allows you to basically tidy up your project, look and see what components you've used, maybe entered into the design and then deleted. It allows you, as I say, just to clear house and make sure you have a nice, neat, clean project file at the end. And then finally, we have the help menu, which I suppose the main part of this is the manual. So if you were using OEMX tool and you had a question and you couldn't get hold of us, the manual is there just as a stopgap, and hopefully you'll be able to find an answer in there until someone came back to you. So that, in a nutshell, is the OEMX suite. We've gone through our requirements, FMEA ArcX, and then FMEDAx. As you can see, it's a very easy process. It's a seamless tool that allows you to move very quickly within each feature built into the suite. So hopefully you've been able to see the advantages of using a commercial tool over a spreadsheet. And as I said throughout this webinar series, not to say is you still can very much do an FMEA and FMEDA through using a spreadsheet, but there are a lot of advantages to using a commercial FMEDA tool. And here are some of the key features to look for, as we've described in previous sessions. Obviously, support for functional failure modes. The embedded component reliability database is a huge advantage. The subsystem analysis, as we saw in our subsystem viewer output, the ability to compare different revisions of different designs, the ability to change operational profiles and have your results automatically update, and a few others there to mention. So in conclusion, an FMEDA analysis can be time consuming. Therefore, using a commercial tool, we identify ways to make it more efficient without significantly impacting results. The information can be invaluable for reliability, availability, and functional safety metric calculation. The FMEDA result is only as good as the component database, and I can't emphasize this enough. Component failure rates vary with design strength, and environmental stress, and the ability to change these within the tool. You're able to see this instantly as the results update. And then FMEDA is done for an architecture design block, which is a series system. Block redundancy is modeled using FMEDA results. So I won't dwell on this screen. As I say, we've already deep dived into the OEMX suite. We've looked at the requirements, the expert knowledge, architecture, and the component reliability, and how it links into the FMEDAx tool. So I'd like to thank everyone so much for your time today, and also thank everyone who's been here throughout the 8 sessions. It's been fantastic. Hopefully you've all gotten something from it. So at this point, I'd just like to hand it over to the floor, and if anybody has any questions.